Okay. So as I was saying that in NMR spectroscopy also, we know that I has to be that nucleus spin state value has to be greater than zero, because if it is zero, then there won't be any interaction, there won't be any induced magnetic field from the nuclei, and there won't be any interaction with the external magnetic field. Similarly, for the MOSFET spectroscopy, there are certain active nuclei and certain isotopes. Say, for example, the commonly known as iron 57, that iron isotope 57, 119 isotope of tin, then antimony, then 129 of iodine, and 197 of gold. So mostly you will be coming across these 4 or 5 isotopes which are giving the MOSFET spectra. There are others also, but mainly we talk about this, and we will be starting with our first nuclear system, which is the iron 57. So now, we know that generally it occurs as iron 5626. So that is the most abundant isotope in case of iron. So this iron 57, the 26, it stays in I equals to half. That's a ground state. And it is having an abundance of 2.14%. That is its natural abundance. That means out of 100%, only 2.14% is 57 iron, rest others is 56. So this much active isotope can only be for the MOSFET spectroscopy. So for these kind of spectroscopy, we need a huge amount of sample. Or a concentrated one. Why? Because already we see that the active MOSFET nuclei, out of 100, only 2% or 2 are the molecules which are going to give you MOSFET spectroscopy. So how the spectra will look like? It won't be having any intensity. For the higher intensity and the proper spectra to be looking at, we need a more concentrated sample. Now the thing here, as we said, that source and the sample, that was our first condition, they should be same in case of MOSFET spectroscopy. So in this particular case, if I'm talking about 57 iron as my sample, the source has to be 57 iron only. But we saw that 57 iron in natural abundance, it exists as I equals to half. That's a ground state, right? And for mass power, the source should be in excited state so that it can emit some energy to the ground state. Right? So if we'll talk about this particular source, that anyway it is less abundant. Secondly, it exists in I equals to half. So that is not going to give you any kind of energy when we are talking about the as a source, because it has to be in excited state and then come back to the ground state so that it can release some gamma rays. So how to get iron 57, I equals to 3/2, that is the excited state. How to get as a source? So that is the question. So what generally happens? Instead of taking iron 57, we take cobalt. This is a radioactive isotope of cobalt, which is having a half-life of 270 days. Which means after 270 days, it will slowly convert to iron 57, 26. How does it happen? You can see there is no change in the mass number, but the change in the proton. That means electron is being used here. So because of the electron capture, that -1 charge. So because of the electron capture, it goes to 27 to 26 and we get excited state iron. I am repeating it again. So we were saying that in case of the MOSFET spectroscopy, our source and sample have to be same. So if I'm talking about my sample has to be iron 57, My source has to be iron 57, first thing. Also, we understood that the isotope of iron in 57, it is having a ground state I value as half. So when we understood that Mossbar spectroscopy, the source has to be in excited state so that it can come to the ground state and release some energy. If it is already at the ground state, how it will release energy? At the ground state, it won't be having any energy. So how to make our source in excited state? So how to make our source in excited state basically? So how to get the iron 57? Naturally, it is occurring as I equals to half. How to get it as a I equals to 3 by 2 excited state as source? So what we do, we have a parent source. We are not starting with iron 57. We are starting with cobalt 57. That's a radioactive source, which is having a half-life of 270 days. That means it can live up to 270 days. And after that, it will slowly convert to iron 57. How? By capturing an electron. So with the process of electron capture, you can see that electron is having minus charge, mass number will remain the same, 27 goes to 26, and we end up having a 57 Rn. Now cobalt exists as I equals to 7 by 2. And we want I equals to 3 by 2 for the iron because that much energy gap only is possible in case of the Mossbar spectroscopy. So what really happens? So cobalt 57, when we have I equals to 7 by 2, T half is equals to 270 days. Now it is radioactive, it will convert to 57 iron 26, which comes to I 5 by 2, and that is also an excited level. Now it goes to, its energy is 136.32 kilo electron volt, very high energy. Now from this it goes to 57 iron 26 I 3 by 2, and its energy is 14.4 kilo electron volt. You can see the difference. Now the difference between these two is 122 kilo electron volt. And we have already explained that for the better resolution, the line resolution, the energy gap has to be very minimum. If this much energy, 122 kilo electron volt energy gap is there, we won't be having any good spectra. So we won't be able to see anything. So this region does not come under Mossbar spectroscopy. Now the last, it can come up to half, which is a ground state. So therefore 0 kilo electron volt. So therefore total energy is 14.4 kilo electron volt. So you can compare 14.4 and 122. So it's a huge amount of energy difference. So only this particular state, which is highlighted like this one, I equals to 3 by 2 to 1 by 2, that becomes a Mossbar active region because that much energy is feasible for Mossbar instrument to detect it. Otherwise, rest of the energy states, the transition is happening, but that energy is not detectable. So we started with parent molecule as this is our parent nucleus, which is giving us an excited iron 57, which we wanted, and it then converts to iron 57. This is the required condition. Iron to be, the I value has to be 3 by 2 because of its energy difference, and therefore we will be having a source. So this becomes our source, the excited state. Is this clear?
Clear, ma'am.
So when we were talking about this, now the question is, how do we get this particular system also? From where we got that radioactive thing? This also comes from 56 iron 26. When we bombard it with the deuterium, it goes to 57 cobalt 27 plus 1 neutron loss. So actually this system is being written as 56 iron, deuterium, neutron, 57 cobalt. So this radioactive cobalt source is also coming from the iron only by bombarding it with a deuterium isotope, and therefore we will be ending up having a cobalt which is required and the neutron. And from the cobalt we get a 57 iron. So these questions are also very important. So the net reaction that we know that okay, from 56 iron when we use 2 deuterium, that's the isotope of hydrogen. Hydrogen is 1H, whereas deuterium is 2D, tritium is 3D. That means mass number is more. So it converts to 57 cobalt, 27 plus neutron. If you count 56 plus 2, it's 58. 57 plus 1 is 58. 26 plus 1 is 27. And 27 plus 0 is 27. So from this parent nuclei, it goes to 57 iron, 26. Why? If it is being taken by a electron capture happens, it loses one electron and goes to 57 nuclei. That is the highest state that I have 5 by 2. Then we convert it into 57 I 3 by 2. That is having 14.4 kilo electron volt, and that is required to have a transition to iron in 57 I half by 2. So this much energy is only feasible. That's why it occurs in the MOSFET region. So clear up to this point, then we can move further.
Clear, ma'am. I understood.
Okay. So now we have another point. Okay, we understood now. We had the source as iron 57, which we claim to be. We want this one. Source in I equals to 3 by 2. And my sample is in, which is naturally abundant, I equals to half. So it's fine. Now, if I'll say my source, it's an excited state already, 3 by 2. So it goes to ground state and releases energy, that's gamma rays. And the sample, which is also the same nucleus, it is in half state, it goes to 3 by 2. Okay. But actually, when this is the condition, when the exactly same energy, okay, the X electron volt is being lost as a gamma rays by source, and X electron volt is being absorbed by sample. So generally we have this matrix, we have put our source in this matrix so that there won't be any much movement. And then we have the sample also in the same matrix. And there is a detector. So detector only detects the rays with gamma rays which are being transmitted. So if X amount is being released and X amount is being absorbed, so there won't be any gamma rays that could transmit. No transmitted gamma rays. So if no transmitted gamma rays, the detector is not going to detect anything. And therefore, we will be having a graph, right? Transmittance, this is 100%, this is 0. So this would be a straight line parallel to your energy, because there is not going to be anything. So in that particular case, what we do, we use a Doppler effect. Because we want some energy to be transmitted and some energy to be getting absorbed so that we can see the spectra. So what Doppler effect does, we can actually fix our sample and move our source in that direction that it can either move towards sample or away from sample. For example, we have this matrix. Similarly, we have the sample. So this is my source. This is the sample. And so this is the detector. So what we are doing actually, here we are Now we are moving this is movable now. This is fixed. And this is also fixed. So if it goes towards the sample, that's a positive velocity. If it goes away from sample, we denote it as minus v. So due to the Doppler effect, now earlier it was E gamma is E transmission, whatever the transition has happened. Now the Doppler effect is there, which is nothing but the E transition 1 plus V by C. That's the velocity with which the source is moving. That's the speed of light. Okay, so why we are doing it? Earlier, when both were in a solid matrix, now there was less peak oil energy, and also the source in sample, source is in excited state, sample is in ground state. So total amount of energy being lost is being taken up by the samples. The absorbance was 100%, transmittance was 0. So we were not able to see anything. Okay, so here in this particular case, the transmittance would be 0. So we will not be seeing anything. That would be a straight line matching the 0 line. Now to have certain kind of absorbance and therefore the transmittance, we are moving our source towards the sample or away from the sample. Just from the Doppler effect, we can change the velocity and therefore we can get some kind of difference in the energies. So now we will understand this concept using the graph. Now, this is my sample. Okay. Now, when I have a source which is, say, for example, earlier it was very far apart, so they were totally absorbing. Now, if my, so this was a scenario, I'm doing it with a dotted line. So this is my sample, this is my source, and this purple one is my sample. This is a case when no Doppler effect. So there would be 100% absorbance. So the area highlighted here. %, absorbance. No peak detected. Okay. Now the next case that we have, if I have now absorbance and my Doppler effect is working, so it goes towards the away from it minus V1. So it is having certain kind of, that is my, so this is a region which is the overlapping one. Okay. So correspondingly, we will draw the transmittance graph also. If absorbance is this much, so my transmittance would be maximum here. So this is minus V1. Just a second. Okay, so this is having, so earlier case, I will draw it with this particular dash line. So this dash line was V equals to 0. So in this V equals to 0, my transmittance was 0 because absorbance was maximum here. Now at V equals to minus 1, there is some portion which is overlapped. Therefore, I am putting my V equals to minus V1. That means it is going towards the left direction. So the next case, if it is having more distance from the your first value, that means it goes from here to here. Now it has moved with velocity v2, which is even more lesser. So there is no overlapping. When there is at minus v2, no overlapping because it is far away. Therefore, no absorbance. therefore 100% transmittance. So my V2 would be here. This is minus V1, this is minus V2. Similarly, now I'm drawing with a different pen. Here, if I have that from this particular direction, if it is going towards the right direction, so if it goes towards here, that's a plus V1 towards the right direction, and here that's a plus V2. So if you'll see here and plus V1, it is having some overlapping. So plus V1 would be here and plus V2 would be here. And now if I'll draw the graph, it would be like this way. This is my plus V1 and plus V2. So this graph is the transmittance versus velocity, millimeter per second. So this graph is between the velocity and the transmittance, and where we saw the Doppler effect and we got a curve like this way. And this is the way the mass bar spectra is going to be looking like. And that is the transmittance versus velocity difference. So, okay. So as you were not here in the meeting, I will explain it again. So up to this point, you understood that we were talking about once the source and sample, they are having same energy, they will absorb the same energy. The source will emit X amount of energy and sample will absorb same amount of energy. They would be 100% absorbance, but we know that transmittance is the that amount of energy which is not being absorbed and that is getting transmitted, that is called as a transmittance. So detector will only be able to detect which energy is not been absorbed and only transmitted. So if it is like X amount of energy being given by source and X amount of energy being taken by sample, there would be 100% absorbance. There won't be any transmission. So our transmission would be, transmittance would be like zero. There won't be anything. So the graph will look like this. So this is zero absorbance graph. This is 100% absorbance graph. So when the case is like when source and sample, they are fixed in a solid matrix, they are moving, they are not moving, and they are emitting and absorbing the same amount of energy. But in this particular case, we won't be able to see any phase, right? So here what we introduce a Doppler effect. Doppler effect is like we will fix our sample and we are now will move our source. Earlier both were fixed. Now we are moving our source. In that way, we can adjust its velocity. If source is moving towards the sample, that would be in addition to that of velocity. And if it is moving away from the source, there would be a less amount of energy which is going to be felt by the sample. So energy is actually related to the velocity of the movement of your source. So this is the diagram that I made. So earlier this blue one, that was a nucleus. Inside this is a nucleus and we have put it in a solid matrix to restrict the recoil energy. Sample also was like this. Now we have made like this you can consider as a wheel. So now we have given the wheels to the source. If it moves towards the V direction, that will give you more energy to the sample, like energy would be more. And if it moves away, that would be a lesser energy. So that increases the chances of absorption, absorbance also and transmittance also. So now the gamma energy that is going to be released, that would be related to the factor of the ED also, that Doppler energy, which is nothing but the 1 plus V by C. V is the velocity of the source and C is the speed of light. So the first case, when there is no Doppler effect, that means are both solid, the source and sample both are in solid matrix. Nothing is moving. So whatever the amount of energy is being released by the source, that is being taken up by the sample. Therefore, 100% absorbance. When absorbance is 100%, there won't be any transmittance. So there would be maximum overlap. Overlap always shows that how much absorbance is going to happen. So source and sample, they are overlapping with each other because absorbance is 100%. Now then other cases. So this is my first case when there is no Doppler effect. So this purple one is my sample energy and the dotted one is my source energy when there is no Doppler effect. But what if I'm moving it away from source? Now the source is having wheels. Now this pen is my sample, and now this is my source. It is moving away. When it is moving away, you can see that earlier it was dash line. Now it has become this line. This is my first case. So this much area only they are overlapping. So this much absorbance has happened, and rest of the amount is your transmittance. So we can consider at V equals to 0. That means when no Doppler is there won't be any transmittance because absorbance is maximum. At V equals to minus V1, that means velocity is minus and plus is only showing the direction. Minus is to away from the sample, and plus is towards the sample. So if it is moving away from the sample, it goes as minus V1, and therefore there would be some overlapping, there would be some absorbance and some transmittance. So some transmittance we kept it like here. Now if it is moving to away, a very far distance from the source, now there is no overlapping at all. So source sample is here, source is here, their energies are not overlapping, they're not resonating. There won't be any absorbance. When there is no absorbance, there will be 100% transmittance. That's why if I say this is 100% transmittance, my V2 would be here. Is this clear up to this point?
Clear, ma'am.
Okay. So similarly, now this was the condition when we were moving our source away from the sample. Now, what if I will move it towards the sample? So now consider this particular case. This was when it is not at all moving. Now, if it moves with the V1 velocity, there you can see the highlighted with yellow. There is some overlapping region when it is moving towards similar amount, that plus V1 would be here, and V2 is far away from your sample. So therefore, there won't be any overlapping, and that would also be having 100% transmittance. So that's why we see the graph like this way. The V kind of shape will come in transmittance versus velocity. And this is actually your Mossbar spectra looks like. So this is the spectra that we are actually talking about, and that is what we need to see. So up to this point, is that clear?
Clear, ma'am.
So the last topic of this particular lecture is we will understand. Okay, now we say that source and sample, they are same. Then how come the energies are coming as different? Why the energies are coming different? If the both source and sample are same. So actually what happens, we mainly talked about if the nucleus is there, it is surrounded by some electron density, right? So that electron density, because it is surrounding the nucleus, that creates a monopole because it's a single pole electron density, and that causes the Coulomb interactions. And that Coulomb interactions make sure there is a deviation in energy states. There would be change in energy state. So whenever there is an interaction, as we saw in NMR, until unless there was external magnetic field, there was no transition, there was no splitting of the energy states. But as soon as the magnetic field is being given, there was a splitting of the energy state. Similarly, when we have this kind of excited states for and ground state for source, so once that Coulomb interaction happens, it goes to high level. So this energy would be, difference would be in a Coulomb interactions, and that has deviated the energy state. Similarly, it happens with the sample also. So this is for the sample. So now the E transmission and the E gamma for the sample and the source, they are not equal. Why? Because of the Coulomb interactions. And Coulomb interactions came when electron interacts with your nucleus. This particular scenario, for an electron or that monopole to exist, so electron nucleus interaction and this Coulomb interactions in short term, it can only occur when both electron and the nucleus, they share the same place. what we are trying to say, that electron should be able to penetrate into the nucleus. So normally what we did is nucleus is there and electron goes into this orbit. They don't come into inside the nucleus. So is there any possibility of electron to penetrate into the nucleus? Do you think that electron can go into the nucleus?
No, ma'am.
So generally we see that it will not. That's a case that we read about. But there is some possibility from radial density function. So we actually see, normally we know in the quantum chemistry, the electron in an orbit, we define it as a wave function. Its movement, we define it as a wave function psi, right? And probability of finding an electron in an orbit, it is defined as psi square. That's your density. These terminologies are clear. So
Probability of finding an electron in an orbit means, ma'am.
when we have an orbit, so when we are expecting that whether this orbit is having an electron or not, that defines, it is being defined as a psi square. So psi is nothing but your wave function, because we know that electron is having this kind of motion, right? So it's a sinusoidal motion. It is having both the particle as well as wave nature. So because of this nature, we define it as a psi function. That psi function, when we square it, it gives us a probability that whether we can find our electron density in that particular orbit or not. So, say for example, there are two rooms. So if I'm saying that boy is in that room or not, what is the probability? There could be 50-50 chances, there could be 10-40 chances, 10-90 chances, or something like that. So probability of finding an electron in a particular orbit, that s orbital, p orbital, or something like that, that is defined as a size. That's a mathematical term. Okay.
Oh, okay, ma'am. I understood.
Okay. So what we have generally, if we take the first s orbital, that is 1s, if you'll start with that one, we have its radial wave function like this way, the psi square, and this is your radial distance. So this distance r, it is the distance from the nucleus. For example, if I have nucleus here and my first orbital is here, 1s, so electron is there. So this kind of distance from the nucleus is r. Okay. Now, how its radial RDF, that radial density function looks like. So it has a probability like this. So if you will see clearly that there is a maxima. So at that particular distance, if it is distance from, like, say, for example, 10 centimeters from the nucleus, and there would be maximum possibility of having the electron density. Like when we say that out of in the room, if a child is having a most possibility of sitting at the center, it is not at the corners, it is sitting at the center. Similarly, if I'm talking about an orbit and at a certain distance from the nucleus, it is having the maximum probability of sitting there. So here we will find the maximum probability of our electron to be present. So there would be having maximum charge density. Clear up to this point?
Clear, ma'am.
Okay. Now, the main point that why I have highlighted here, if you will see here, in this particular region. So here we are having psi square not equals to 0, even when r is equals to 0. Right? So r equals to 0, that means it's nucleus. That means no distance from the nucleus, that means it is a nucleus. And psi square is not equals to 0. It is having some finite value. So that means there is a possibility or probability of having that electron density penetrating into your nucleus for certain time, and that is defined from your radial density function. That's why s orbitals have the tendency to penetrate into your nucleus. So the concept of having no electron density inside the nucleus is not at all true. if we see the radial density function, we have certain kind of finite probability of having that electron density penetrating into the nucleus. So when that electron density penetrate into the nucleus, it creates a Coulombic interaction, and because of the Coulombic interactions, we saw the changes in the energy state of the sample as well as the source. And because of the different changes happen at the source and sample, even though they are same, we saw different absorption and the energy levels. Clear up to this point?
Okay, ma'am, I understood.
Why we were saying that whether in nucleus we can see some electron density or not, that comes from the radial density function. Now, if we'll see some other orbitals. Now, say for example, if I have taken this 2p. Now, I'll consider the 2s and 2p. So 2p would be R. Now 2s would be like this way. Having one node, we know that as the progress of the orbitals, there would be number of nodes also. So 2s would be having one node, and 2p would be like this way. So this is your 2p, and this is your 2s. So again, the 2s, if you see here, in 2s orbital, again psi square is not equals to 0 at r equals to 0. That means again the certain electron density from the 2s orbitals can penetrate into your nucleus. Whereas in case of your 2p, that radial density function, psi square is 0 at r equals to 0. Therefore, p orbital electrons, they can't penetrate inside the nucleus. So only the s orbital electrons are the one which can penetrate, which have the probability of penetrating inside the nucleus. So clear up to this point? Is there any doubt here? So these wave functions and the psi square, they comes actually from the quantum chemistry. If you have any doubt, you can go back and check the mathematical forms where psi square, we are not giving any assumption. Psi square coming as a finite value as a function of r, that is coming from a mathematical equation. So this is all been defined well in the quantum chemistry. If you can see for the 2s graph, at r equals to 0, psi square is 0. So at this particular moment, there would be no electron density penetrating into the nucleus. But if we'll see at r equals to 0 over here, no, so this is not r equals to 0. If r equals to 0 over here, we have certain electron density. So inside the nucleus, there is certain distance. But if we move a certain distance, say for example, x centimeters from the nucleus, there would be like no electron density is present. That is called as a node, when there is no electron density present. So in 2p orbitals, d orbitals, f orbitals, there won't be any penetration of the electrons into the nucleus. Only the s orbitals, they are having psi square not equals to 0 at r equals to 0. That means they have the probability of finding an electron from those orbitals into the nucleus. So is this clear?
Clear, ma'am.
Okay. Okay, great. So this was the main thing, and then we will talk about actually these kind of terminologies is related to when we understood that okay, some penetration is happening, the Coulomb interactions are there. So for this, we have certain assumptions to formulate, because we need to have certain formula from where we can say that okay, the penetration is happening, how much it is affecting, how much Coulomb interactions are occurring. So the first assumption, we consider that nucleus is spherical, and also the radius from the nucleus, we consider it as a r. So that is the thing. Now energy or the Coulomb interactions would be having certain energy that would be having Hamiltonian. So it is given as 2 by 5 pi Ze square psi square r square. Don't worry about this much. So Ze